Hey guys, today I'm going to walk you through the two-way frequency table tutorial. I'm going to skip those first couple slides and then skip right to this introduction. This talks about a screening test in the medical industry, and this just tells you whether you're at higher risk for certain diseases and whether you should undergo further testing. They're not diagnostic, but from this information that we get, you can create some two-way tables. If you want to read about the screening test, you can click on that link and it'll take you there. But this section is all about a two-way table, which this right here is an example of a two-way table. And what it does is it allows you to compare two variables and four possible outcomes. So here, the screening test is for cholesterol. So they're going to screen your cholesterol level. You can either have normal or high, and then they're going to figure out whether you have heart disease, either yes or no. So these are the four possibilities. Here is a knowledge article, just like in all the other ones that you can read. But we're going to kind of talk about all of this as we go through the activity on the next page. So looking at that same frequency table, the first thing we're going to do is figure out the probability of having high cholesterol. Okay, so now what we need to do for this one is, first of all, recognize that the total number of people who were screened was 750. The total number of people participating will always be in that lower right-hand column, or that lower right-hand cell. So there's 750 people total. The total number of people who have high cholesterol, I'm going to come in the high column, it's going to be 372. So that probability is going to be 372 over 750, which, if you do a decimal approximation, is 0.496. So you have about a 49-50% chance of having high cholesterol. Not that great, but move it on. Now we're going to figure out the probability of having heart disease. So if we come over here again, the total number of people is 750, but the number of people that have heart disease is 234. So we're going to do 234 divided by 750. And if we use a calculator, we'll see what that is. 0.312, or about 31.2%. And that's your risk of having heart disease. Number 3, now we're going to figure out the probability of a patient having heart disease given that they have high cholesterol. So when you have this given statement here, there's two ways you can do this. You can either use that formula we used a while ago, but I'm guessing most of you have forgotten that by now. But what I like to do is I like to just limit the sample space. And this is going to be my sample space. So if I go up to the table, the number of people that have high cholesterol are 372. So now I'm only going out of 372 people possible. And then we want to know what's the probability of heart disease. Well, of those, heart disease was 223. So our probability is going to be 223 out of 372. And again, that's just restricted to just the people with high cholesterol. And that's going to be 0.599. Okay, so they kind of walk through that first way of figuring it out. You can do the probability of A and B divided by the probability of B. But I like just restricting the sample space. It's a little bit faster. Number 4. Using the table, we're going to do the same thing now, but figure out the probability that there is no heart disease given that they have normal cholesterol. So up to the table, now I'm looking at normal cholesterol as my sample space, which is 378. And no heart disease is 367. So this is going to be 367 divided by 378, which if you use your handy dandy calculator, is 0.971. So that means if you have normal cholesterol, you have about a 97% chance of not having heart disease. Okay, so it sounds like you should probably try not to have high cholesterol. For number 5, we're going to fill in this chart. And again, this number right here, this 650, is going to be super helpful. That's the total number of people. So I could fill in right here that needs to be 50. So this whole row is 50, which means the number of negatives right there is 7. And then I can add 7 and 567 and get 574 for that column. And then if I subtract these, because I know that these two numbers have to add up to 650. 650 minus 574 is 76. And if I do 76 minus 43, I know that this number has to be 33, or you can just double check that 567 and 33 is 600. Okay? So just double check that that table looks right. And it does. Okay, so there's our table, and now we're going to answer, I think, just one question on it. the probability of a false negative given that there was a negative result. So this is the probability of a false negative given that there was a negative result. So that whole given thing, that means we are restricting our sample space to just the negative result. Okay, so that means my denominator is going to be the negative result, which is 574. There are 574 negative results. Okay, now when you think of a false negative, you have to figure out which of these options it is. So a false negative means your test result said it was negative, but it was actually positive, it was actually present. So that's going to be that 7. Okay, because if you got this 567, they got a negative result, and the disease actually was negative. Okay, so that's why we need to do the 7 people that got the negative result but actually had disease, which is about 0.012. Okay, so about a 1% chance of a false negative. Okay, I 5 on the self-eval, and then moving on. So this slide right here just basically kind of reviews when you have those conditional probabilities, you can use this formula, but I like to just restrict the sample space to a specific column. And now we got a problem here. I didn't mean to do that. Okay, well, that was an accident, but let's just read it anyway. Based on this two-way table, what is the probability of a false positive given that the test is positive? So I'm just going to reload this. So, given that the test is positive means I am restricting myself to just those 247 positive test results. Okay, and then a false positive, you can read this here, says the test result is positive, but actually did not have the disease. So you need to have a positive result, but did not have the disease. So it's actually going to be 37 over 247. And there I didn't make a mistake and I clicked the right thing. Okay, so that's slide 8. Slide number 9 says another thing that we can do, use two-way frequency tables for, is for independence. And I just want to remind you that for independence, if the probability of A given B equals the probability of A, that means the events are independent. Okay? If the probability of A given B does not equal the probability of A, then the events are dependent. Okay, and again, I missed my smartboard. But coming back over here, in this activity, we have to first of all fill in this table. So it says here that of the 150 people who identified as Democrats, so that means identifying as Democrats, the total is 150. 133 said they would vote for the Democratic candidate. Okay, now that means that we should have 17 people left over to vote for the Republican. And then it says of the 160 people who identified as Republican, 142 said they would vote for the Republican candidate. So that goes right there. Which means if you do 160 minus 142, you have 18 people who are going to vote Democrat. If you figure out our total, you can add 150 and 160, which will be 310. And you can just keep adding straight across these rows. And hopefully everything looks good there for our table. Great, we got our table. Now for number 2. We want to use the table to determine the probability that a person will vote Republican given that they're a Democrat. So given that they're a Democrat means we're going to look at 150 as the denominator. And the number of people that are going to vote Republican is 17. So over here I'm going to type 17. So 17 over 150, which as a decimal is 0.113, or about 11% chance. Yay. In 3, we're going to figure out the probability that a person will vote Republican given that they're a Republican. So if you look over here, given that they're a Republican, it's 160 total Republicans. The ones that are going to vote Republican are 142. So this probability is 142 over 160, which is about 0.888 or 89% chance that you're going to vote Republican. Now we want to know, is being a Democrat and voting for the Democratic candidate, are they independent? So what we're going to do here is you just pick one of them to start with. I'm just going to start with the probability of being a Democrat. The probability of being a Democrat, if we look here, there's 310 people and 150 Democrats. That would be 150 over 310, which in our calculator is 0.487. Not a decimal, 0.487. Then we need to figure out the probability of being a Dem. Actually, hold on, I did my number wrong. 0.484, my apologies. So now we're going to look at the probability of being a Democrat given that you are voting Democrat. Okay, so now the number of people voting Democratic are 151, and the number of Democrats are 133. So it's going to be 133 over 151, which equals 0.881. Okay, and remember, according to this formula, if they're equal, then they're independent. If they're not equal, then they are dependent. So these are they are not equal. So these are dependent events. Okay. And I just want to point out that here, they kind of did it backwards. They put the probability of voting for a Democratic candidate and then the probability of voting Democratic given that you're Democratic. It doesn't matter because the two probabilities are different anyway. So they're still going to be dependent events. Okay, and that just basically means whatever political party you're in is going to influence who you vote for, which kind of makes sense. All right, and then on this last table, we have the people that use mass transit regularly and their age. So here we're going to find the probability that they use mass transit given that their age is 30 or under. So given is my denominator. There's 575 people that are 30 and under, and those that use mass transit is 125. So this will be 125 over 575, which if you use your calculator, 0.217. What's the probability that you will use mass transit given that you are under 30 or under? For number 6, the probability that your age is over 30 given that you do not use mass transit. So not using mass transit, there's my sample space, 675. That's my denominator. And then we want to see of those 675, how many are over 30? And that's 225. And then again, we work that out. 225 divided by 675 is 0.333. So if you don't use mass transit, you got a 33% chance of being over 30. And then finally, last question, 7, are mass transit and being over 30 independent? So what we have to do, figure out, find the probability of one of those first. I'm going to find the probability that they use mass transit. And if you do that, there's 425 people total who use mass transit and 1,100 people, the whole table, because remember 1,100 is this, 425 use mass transit. So that probability is 0.386. Okay. Then we want to find the probability that they use mass transit given that they are over 30. And so when we do this, this is going to restrict my denominator to 525, and there are 300 people over 30 that use mass transit. So 525 is going to give us about 0.571. Again, I got those numbers from up here, that the total number of people over 30 is 525, and of those, 300 use mass transit. Now, independent, yes or no? The answer is they are not independent because these two numbers are not the same. So these would be dependent. Okay, not independent means the same thing as dependent. All right. I don't know why that answered right away, but let's take a look at this. Here we have another table, and we have to select the correct answer to figure out. If you look at the choices, they all say independent, dependent. So I'm going to come back to this formula. Probability of A given B equals probability of A. So right away, what I can do is I can eliminate this answer as a possibility because that's not the formula we use to figure out dependence. And then that's the only one that I can do right away. But if I look here, this is saying that they're not equal, and it's saying that they're independent then. But remember, if they're not equal, it actually means that they are dependent. So these middle two I can kind of eliminate. This fits the bill. Independent, that's the right setup. They would be equal. This is dependent, not equal. So between the first and the last one. So what I need to do is calculate the probability of preferring fiction, given that they're female. So that would be 100 over 120, which would be 0.833. And then just the probability of preferring fiction would be 140 over 300. At 140 over 300, which is 0.467. So this doesn't work. Over here, let's try this one because they're not equal. Let's try the probability of preferring fiction, given that you're male, that would be 40 over 180, which would be 0.222. And then the probability of preferring fiction would be 140 over that 300, which is 0.467. And those are not equal, which means that that is correct because they are not independent, they are dependent. And yay, we got it right. Okay. And so in summary, this just kind of talks about what we can use the two-way tables for. Here's our gold star, and you guys are all set, and now you can go do your mastery test. Remember, don't take like 10 seconds on the mastery test. Take your time. If you have any questions, let me know.